Okay, so hopefully you can see my presentation.
Yep.
Okay, so welcome everyone to this seminar. So this is one of several seminars CIGRÉ Ireland is doing this year on each of the study committees. So this one is on B4, which is DC systems and power electronics. And just you would have probably got it as you logged in, but we're going to record this and eventually it's going to make its way on to YouTube. So just, you probably all know what CIGRÉ is, but just officially, its purpose is to foster engagement and knowledge sharing among power system professionals globally to enable the sustainable provision of electricity for all. So it's a not-for-profit organisation. It was established 100 years ago in Paris in 1921. It has 59 national committees. The Irish National Committee was established in 1955, and it's got 15,000 individual members and 1,200 organisational members. So this slide shows the different study committees that make up CIGRÉ, which is a big part of CIGRÉ. So on this, there's 16 study committees in total, and under each of these study committees is the Irish member for those study committees. So as you can see, we've got members on most of the study committees. I think there's 2 or 3 that we don't currently have one on. And this presentation is going to be on B4, which is down here. Yeah, it's highlighted there. So B4 is DC systems and power electronics. Its mission is to facilitate and promote the progress of engineering and the international exchange of information and knowledge in the field of DC and power electronics, to add value to this information and knowledge by means of synthesizing state-of-the-art practices and developing recommendations. So B4 is a technological study committee, and it focuses on 2 areas: DC current equipment and power electronics for AC systems. So the first one is HVDC interconnectors and things like offshore DC grids, and the second one is more in the field of FACS. So that's STATCOMs and SVCs and triple SCs as well. So B4 itself is chaired by Joanna, and the secretary for B4 is Rebecca, and they're both based in Canada. There's 24 regular members, including myself for Ireland. There's 4 additional members, so some countries, maybe Canada and China, for example, have kind of 1 member and an additional member. And there's also 11 observing members as well from 11 other countries. So yeah, the Centennial Paris 2021, there are a few awards for B4 there. There's Mohammed Rashwan was made a CIGRÉ Fellow. So that's quite a big deal. There's only 5 fellows made every 2 years. So he was the study committee chairman for B4 before Joanna, and he's had a long career working on B4. And also in Paris 2021, Ting An from China was made the CIGRÉ got the B4 CIGRÉ Technical Council Award, and she's done a lot of work for B4. So this is an award to recognise her. And also, we're going to have CIGRÉ 2022 next year. And just to thank Georgios from UCD, he submitted a paper that's been accepted for B4 from CIGRÉ Ireland, and his paper is the assessment of the frequency estimations provided by a prototype phase lock loop. So that should be a very interesting paper, which I'm looking forward to reading next year. So yeah, key to all the study committees is the working groups. So currently, a working group is formed when there's some issue associated with the study committee's area that needs investigation. And the study committee is formed of a group of experts, global experts, and they come from vendors and especially for B4 owners of power electronics, for example, and also there's academic input and also from some government kind of scientists, engineers as well. And so they form a team that investigates the problem, and then they come up with recommendations. And these recommendations are produced in a technical brochure. So we have, B4 currently has 14 active working groups. There's 7 joint working groups that are with another study committee. So these are an area that kind of crosses the boundaries of the areas of two study committees. We also currently have 1 joint working group, which is with the IEEE. And then we've also got 1 task force, which is actually a joint one with B1, which is the cable group, which is this 4th one down here. So a task force is kind of like a mini working group. So a more kind of restricted area or more defined scope and a shorter turnaround. So like a working group might take, between 3 and 5 years to report back. A task force, I think, is between 1 and 2 years. So on this page, the little Irish flags on the various working groups, those are the ones where someone from CIGRÉ Ireland is working in that working group. There's one green one here, this flexible AC transmission systems. That's a working group that is almost finished its work and the technical brochure is out soon. There's a second page here, which is, there's actually older working groups, and there's 4 of them here at the top, which are also imminent. So there should be a technical brochure for those ones coming out in the next 6 months or so. Right, so as I said, one of the main outputs of the working group is this technical brochure, which is a kind of a document that explains the recommendations. So in B4, in the last, so far, because there's probably going to be more this year, in the last 2 years, there's 7 have come out. One of those was with C2. And as you can see, the 7 of them are on this page, and 2 of them had representation from Ireland on the working groups. And also last year, B4 produced a green book, which is kind of like a textbook, and I've actually got it here. If you want to see it, what they look like, upside down. Oh, and yeah, that was produced as well. So if you're a member of CIGRÉ, you can access pretty much everything off this ecigré.org. So if you're a member, then you can access all the technical brochures and other publications that are produced. I think the only thing you can't access on that, or you have to pay extra for, is the green books. And so yeah, this ecigré.org is, and it's one of the great benefits of being a member of CIGRÉ, is having access to that. So yeah, anyone who's in CIGRÉ Ireland can work in a working group. So the way that happens is every 4 to 5 times a year, new working groups appear, and if you remember, you'll get an email from Mark, and actually he sent one last night, and this is that email. So, and it says what the working groups are. In this case, there's 2 working groups for C4, both associated with lightning. And if this is like an area that you're interested in and want to work on the working group, there's details in the emails about how to join that working group. And there's, yeah, it's just if you're ESB or EirGrid, there's special kind of rules or people that you should contact in your organizations before going on a working group. Okay, so just, yeah, there's in CIGRÉ Ireland, there's a next generation network, which is for younger members of CIGRÉ, which are those under the age of 35. So they're quite active. They're very active actually. And yes, you get quite a good discount by being under 35. It's only €45 to join CIGRÉ, which is a 50% discount on the individual membership price. And Jason, who's hosting this, was helping out with the Zoom call here. He's a member of the Next Generation Network. And if you want to know more information about that, they have an email address here, cigrengn@gmail.com. Okay, so that's almost it for me. So just a kind of a highlight of what's coming up. So we've got Marie and Robert, who we introducing smart wires and talking about their power electronic offerings. And then after that, we've got Sam and Nathaniel, who will talk about Ireland's oldest HVDC link, which is the Moyle HVDC. And it recently had a midlife upgrade of its control system, so they're going to cover some of that. And then it's not actually built yet, but it's well in progress, and that's Jonathan, and he's going to talk about Greenlink, which is going to go from County Wexford across to Pembrokeshire in Wales. And then finally, last but no means least, is Karl O'Keeffe from EirGrid, who will talk about interconnectors in Ireland, the past, present, and future. So just the format of the presentations. So there's 20 minutes allotted for each one. So the first kind of 15 minutes is going to be the presentation, and then we're going to have 5 minutes at the end for questions. And the way we're going to do questions is in Zoom, there's a kind of a reactions button that you have at the bottom, and you'll be able to raise your hand. At which point, you know, I guess there'll be several people raising their hands at once. The presenter will, you know, acknowledge you, in which case you'll unmute your microphone and ask your question. And just a reminder that if you're, you know, if you're not talking, please mute your microphone, because we don't want any accidental background noise from cats or children, of course. Okay, so that's it from me. So I guess on to Marie.
Great, thanks. I'll just share my screen now. So hi everybody, I think I probably know a lot of people on the call. Those of you who don't know, my name is Marie Hayden and I'm a Chief Engineer with Smart Wires, and myself and Rob Fenlon, who's our Senior Application Engineer, are going to talk a bit about how Smart Wires is using power electronics to maximise grid utilisation and stability. So Geoff mentioned there that in the power electronics field, we look at DC systems like HVDC, and the other presentations this morning talk about that. And we also cover fax devices. So Smart Wires is in the fax devices family. Just to go on, for those of you who don't know Smart Wires, the company is headquartered in the United States, but we do have a global workforce, and we have the European headquarters located here in Ireland, where we hire about 30 people, and we have staff located all around Europe, Australia, America, and South America. We also have a very global customer base with installations in the countries you can see there. And we have about 300 people in total working for the company. Our area of specialty is in power flow control technology. And I'm just going to give a quick overview of what power flow control is trying to do on transmission grids to help maximize their usage. So this is a fairly simplistic representation of a transmission system. And if you look at the box on the left and look at what we're trying to depict here, it's the fact that the transmission systems operate in parallel. It's a mesh network, usually trying to connect generators to demand. And if you think about this in the context of Ireland, you could imagine the generation in the west coast, the wind, and then all of the demand in the east coast, where Dublin is and all the data centres are, and a meshed grid in between made up of 400, 220 and 110 kV lines, all of different sizes, lengths and construction type. This grid has been built up over nearly 100 years, and one of the characteristics which is common across all grids is that the amount of power that will flow down a power line is determined by its impedance or its resistance. And what we see here is quite a typical situation where one line, which is pretty low impedance relative to the other circuits, is carrying the majority of the current and is in fact getting overloaded. And this then causes a bottleneck on the grid, or a constraint as it's often called, or congestion. And the problem is, once you start hitting this bottleneck, you can't really increase the generation in the west, because the more you try and transfer across from west to east, the more you're going to overload that circuit. You can see on the other circuits, though, that there's plenty of spare capacity on those. So what power flow control tries to do is to get access to that spare capacity on the underutilized lines by controlling the impedance of the different lines in the meshed grid. So when you look at what's happening with the Smart Wires equipment, we can do both increases and decreases of impedance. So if we increase the impedance of the line that's overloaded, we can push power off it, and it'll naturally flow onto the other parallel lines. And we can encourage that even more by decreasing the impedance of those circuits by operating in a capacitive mode, or a pull mode, as we often call it. So this combination of pushing power off overloaded lines and pulling power onto underutilized lines can unlock significant amounts of capacity on the grid without the need to construct new overhead lines. And again, another example of this, when we go and look at the Irish grid, is the application of series compensation to the 400 kV network between Moneypoint and Dublin, which is looking to do exactly this, to reduce the impedance of the 400 kV network, to encourage power to flow along that network, which is underutilized, and to divert it away from the overloaded 220 and underlying 110 kV network. So just to talk then about how we use power electronics and a little bit about the evolution of the technologies that SmartWires has been developing. So we're on our third generation of technology, the smart valve, which you can see at the bottom. The first two versions of our technology were in fact magnetics based. So we were not really using power electronics to control the impedance of the line. And both of these technologies used magnetics to increase the impedance of the lines to which they were connected. So they only had the capacity to increase. They were like distributed series reactors or big inductors, and they were pushing power off the lines to which they were connected. If you look at the middle picture there, that's an installation in UKPN, where installing this equipment on the, I think it was the 132 kV grid, got about an additional 100 megawatts of transfer capacity across 3 circuits by balancing them out. But we did start to hit limitations in terms of scale of application when we were using magnetics, and of course in terms of cost as well. And that's when we started to invest in moving over to an entirely power electronics based power flow control technology. And we resurrected a technology that had been first investigated on power systems in the 80s called static synchronous series compensator. A bit of a mouthful, so we always just call that a SSSC technology. And we made a significant number of changes to that technology, taking advantage of changes in the capability of power electronics over the decades. And we now have a world-leading product of modular SSSC technology deployed on grids around the world. And that picture there is from National Grid, where the technology is installed at 275 kV and 400 kV. And of course, in fact, exactly the same equipment is also installed at 330 kV. Our installations at the moment, the highest voltage we're at is 400 kV. We have a 500 kV installation in South America next year. So the SSSC technology, unlike our predecessors where we were using magnetics to physically change the reactance of the lines, what we do with SSSC technology is we create a voltage waveform and we inject it into the line in series with the line and 90 degrees out of phase with the line current. And that has the effect of increasing or decreasing the impedance. The beauty about using power electronics is you can either go lagging or leading the line current by 90 degrees, and that allows you to move from an inductive mode to a capacitive mode very seamlessly. So you can either push power off or pull power onto that line, depending on what's happening on your grid at that time. The electronics which enable all of this is a combination of voltage source conversion technology, and I'm sure you'll hear more about VSC technology in the subsequent presentations. It forms the basis of some of the HVDC interconnectors. And that is made up of IGBTs, transistors, which control the amount of voltage we inject into the line. So I'll show a single line diagram to try and go talk through that a little bit more. Just one thing I want to say is just the scale of the increase in impedance control we have achieved over the last 5 years with the technology. So we are now with the Smart Valve 10-1800, which has its first deployment next year, injecting about 500 times more impedance from that device than we were from a Powerline Guardian 5 years ago. So that's a really dramatic increase in capability. We are operating up to 3,600 amps continuous in some installations, 1,800 amps in other installations, and we have a fault current capability of 63,000 amps, but also the capability to increase that to 80,000 amps where it is needed. So second last slide here, just to talk a little bit about the technology itself and how we use the power electronics. So in the bottom here, you can see with the part of the smart valve, which in fact is where we inject the voltage. So we use these IGBTs to control the charging and discharging of a DC capacitor, which gives us our voltage wave. We can control the timing of them to minimize the impact of harmonic distortion on the transmission system. And we can control the magnitude of the voltage injection from 0 up to the maximum voltage injection from this device and anywhere in between. And so that is independent of the line current. And that's a significant flexibility that you don't obtain with a number of other technologies like series capacitors. You don't always want to be adjusting the impedance of your line. You may, in fact, want to only use this when you're in a post-contingency event or you have a particular overload. And so we use these vacuum switches, these vacuum interrupter switches, VSLs, to operate in what's called a monitoring mode or a bypass mode. And that gives the system operator the flexibility to not inject at all by closing the VSLs. And these provide a lower impedance path to the IGBTs, and we put the IGBTs in a blocking mode as well. And that prevents us doing any voltage injection. So it's almost like we're basically a short for the transmission line. The transmission line comes into the device, goes straight through the VSLs and straight back out again. When we are in injection mode, one of the limitations of IGBTs is how much fault they can, how much current they can handle. The IGBTs we use can handle up to 1800 amps, so that's a significant amount of current to put through IGBTs, and in fact over 2000 amps in overload conditions for a few hours. But they're not designed to carry high levels of fault current, the sort of 63,000 amps we talked about earlier on. And so we use silicon controlled rectifiers to handle fault current, and we use a very sophisticated, speedy fault current detection system that activates or fires these SCRs within about 1 microsecond of a fault being detected, or I should say an overcurrent being detected, to be honest. So we're talking about faults maybe out on the grid where all of a sudden the current coming into the line increases very dramatically. It's detected by our current sensors, and they fire the silicon controlled rectifiers, which are designed to handle tens of thousands of kiloamps. And these devices then fire for about, as long as the fault is on the system, up to about 1.5 seconds, at which stage the power system protection will have cleared the fault. And at the same time as these are firing, we also close up these VSLs. So we have a second path for the fault current through the VSLs. So that's really the fundamental power electronics components of the device, the SCRs and the IGBTs. And then, of course, we use very sophisticated firmware and software to control all of this and to maintain things like the phase lock loop so that we stay within 90 degrees exactly of the line current. One of the big benefits of using power electronics is they're highly controllable and they can respond in, as I said, microseconds or milliseconds to system events. And that means that in addition to being able to provide steady state or post-contingency power flow control to manage overloads on systems, which typically need to be managed in the order of seconds and minutes, this device can also use its voltage injection capabilities to respond in micro and milliseconds to system disturbances, effectively helping improving the transient stability of the grid. We see the smart valve as a platform, a bit like an iPhone, and we can develop additional applications that run on it to supplement the power flow control. Again, one of the beauties of operating in a digital world where you're talking firmware and software instead of hardware is that we can develop these applications, these software code, and we can upload them over the air onto already installed devices. So as we develop more applications, we can upgrade our existing installations for our customers so that they can do more in the future. And Rob is going to talk a bit about some of these applications as well in his presentation. So I'm going to stop sharing and I'm going to let Rob take over now and share his presentation to talk through some of our examples.
Cool, thanks, Marie. What I have on screen here is one of the applications Marie was talking about at the start. She was talking about resolving thermal overload specifically on transmission grids. On the left-hand side is shown a simplified diagram of where you end up reaching the thermal limit of a line under certain contingencies. In this case, it's 2 parallel circuits. This specific case study was when a utility wanted to increase their renewable connections in one location in the country, and they had drawn a number of boundaries across the country and wanted to increase the transmission capacity across those boundaries. The issue is that there was uncertainty in the timing of the connection of generation and demand, and the traditional solutions, reconductorings, PSTs, operating of transformers, things like that, didn't provide the same level of flexibility that you could achieve using the SSCs. So the bottom diagram shows kind of the overview of the solution here, where multiple SSC installations were used, some directly on the overloaded assets, like Marie was talking about, pushing power onto the underloaded assets, and some directly on the underloaded assets, pulling power across different paths to increase the transfer capacity across those boundaries. The solution here found that using multiple small installations was more effective than one large installation in one location, as there were challenges with siting, cost, and the length of outages to do those types of deployments, whereas multiple small deployments reduce the length of outages, and the fast delivery of the SSCs themselves compared to the PSTs and the reconductoring reduce the sort of disruption to the grid as well. And the impact that this had overall, this set of triple SC installations, was to increase the transfer capacity across a number of different boundaries by 1.5 gigawatts. And that effectively amounted to about 387 million listed here, pounds in saving passed to the customer in reduced congestion costs effectively. And the advantage of this was that once this solution was employed once in the existing grid, it could be applied multiple times around the grid, because there are multiple locations where this boundary condition exists, where there's a limit to the amount of transfer capacity going across those boundaries. The exact scenario that I was talking about here was the deployment in National Grid in the UK. On the left-hand side here, you can see the transfer capacity, the energy basically being transported from the north of the country, where a lot of the renewables are connected, to the south of the country. And each of these green lines is where each of those boundaries are. And we focused on a particular set of boundaries in the middle of the country, or the SSE installation was installations were on the set of boundaries in the middle of the country. And as you can see here, there were mainly smaller deployments. The largest deployment was 135 MVA on 275 kV network, but most of it was below 60 MVA installations here. So small incremental changes around the grid had a much larger benefit in this direct power flow control application of a SSE. And you can see on the bottom here is what each of those installations kind of look like. The first three are ones that were fully constructed, and the last two were photos taken during construction. Mounted directly onto the insulators, connected at line potential without any injection transformer as well. So that was the application of this SSE solution. The next application that I want to talk about is improving stability limits, particularly focusing on voltage stability. So this was an application studied in Australia, in the southeast of Australia, where there was meshed grid connected radially to generators, and basically they had reached the voltage stability limit, and also they had issues with angular stability as well, but I'll focus on the voltage stability application, where the utility wanted to increase the transfer capacity by 300 megawatts. Building additional lines was going to be infeasible due to the cost and length of the actual lines between the generators and the demand centers, and this was also across a state boundary as well. So the solution with the SSEs basically reduced the series impedance of the line. It injected like a series capacitor, injected a voltage similar to a series capacitor, and cancel out some of the line inductance, and then pushed out the voltage stability limit. So pushed out the nose of that power and voltage curve. It solves the problem without the limitations of SSR compared to the series capacitor solution that was proposed. And then also there was an SVC solution proposed for the same solution for the same problem. And it was more cost effective than that due to the size of the SVC required. The basically impact that this studied solution would have is it was going to increase the transfer capacity by 300 megawatts, and also reduce as well the dependence on local peaking units, and reduce the cost of electricity in the demand center region. And then looking specifically at how this works, on the right hand side you have that curve showing the relationship between the power and the voltage, the transferred power and the voltage. The compensating, the level of compensation here shown as XC. As you increase the level of compensation, you push the nose of that curve out and can increase the transfer capacity of that line. So the problem statement here is that these long lines ended up with a limit here where you have either drop in voltage or pushing the voltage into an unstable region as you try to push more power down that line. The comparison to the two solutions proposed, or two of the solutions proposed, was comparing it to series capacitors, which would have done a similar job of decreasing the line reactance. There were issues with SSR identified using series capacitors, and you were able to mitigate that using the SSE. Sort of the two main points about that were the SSE, as Marie said, injects in quadrature with the line voltage. If it injects in quadrature, your subharmonic frequencies injected should effectively be zero. And then the capacitors in the SSE are much lower rated than those inside of a series capacitor. So that ripple that you would get at those subharmonic frequencies as well should be much, much lower as well. Those are just two of the the impacts are how you reduce SSR using a SSC. And then the impact on existing protection. So Marie talked about this fast bypass. So SSCs can be installed with the fast bypass technology to avoid impacting existing protection systems. And they can also provide additional control services as well. Instead of just providing bulk voltage injection, they can react dynamically to things going on in the grid and provide additional services. Comparing it to the SVCs as well that were proposed, there was less MVA required. So the SVCs had to have a much larger installation on site than compared to a SSC solution. The SSC can be scaled up and scaled down a little bit more easily than the SVC, as the components use, series reactors and series capacitors, reactors and capacitors. And then the SSC was also able to be installed sort of anywhere along that circuit. So at the sending end, at the receiving end, or in the middle of that circuit, it doesn't really matter because the compensation level, it's going to cancel out some inductance somewhere. It doesn't really matter where you put it, whereas the SVC has to be installed at the receiving end bus to have the same net effect. So those are just two applications that I wanted to discuss or explain how the benefits of the SSC there, and that's sort of the end of the presentation that we have there. So if there are any questions that we have from the group.
Geoff, I think you have a question.
Yes, it was just on the you had the bypass for the whole device. Do you have submodule bypasses as well?
We do actually, yes. So in the latest version of the technology, what you see here, hopefully you can see my screen. This is a single line diagram representation of the smart valve. And in fact, it's not just one voltage source converter, it's multiple converters. This is actually the 3600 amp version. So we run two 1800 amp paths in parallel. In the 1018 version that we're releasing in January, we run the 10 converters in series, so we get double the voltage injection. It's only up to 1800 amps. Each of those converters has an option in the technology to be individually bypassed. So if you have a fault on one converter, the other 9 converters can remain injecting without employing this major bypass system here. So at an individual SSC module level, you can have bypasses on the individual converters. And then when you look at the sort of installation here, where you've got, in this case, 2 per phase, but we have installations with up to 7, 8, 9 per phase. If one of these is bypassed, the other 8, 7, 8 are all still actively in series. So if you don't look for that converter level bypass option and you just go for a modular level bypass, the remaining devices remain in service, and then we have a control system which will balance that across the 3 phases, because this is a single phase device. So you can bypass at a modular level or at a converter level, and that's really good for not having a single point of failure. So if you do have a problem with the valve, you don't lose your whole installation, you lose a percentage of your installation. It's one of the benefits of modularity. I hope that answers the question.
Yes, thank you.
Thank you. Anything else? I managed to not use too much time, Rob. I think we almost stayed on time. I'll let you go on to your next presentation. If anybody does have a question, you know how to contact us, or even throw something in the chat window. I'll be happy to answer.
Okay, thank you, Mary. So yeah, I guess we'll get on with Sam and Nathaniel about Moyle.
Good morning, folks. Bear with us just a moment or two because we're much more familiar with Teams than we are with Zoom. So apologies if there's any minor interruptions here. Let's see how this goes. Okay, hopefully that'll get us onto PowerPoint. Okay.
Oh, you're sharing the presenter view, Sam.
That's what I was worried about. Okay, bear with me 1 second. We'll keep it simple.
Sorry, Sam, if you go back into that view and you can just change the display over to that screen.
Yeah. Yeah, perfect.
Okay, so you're seeing the title screen now, hopefully.
Yep.
Yep. Okay, great. Okay, folks, apologies for that delay. So my name's Sam Gibson. I'm the operations manager for Moyle Interconnector, and we have alongside us here Nathaniel Cowton, who's our project manager for the control system upgrade. I'll take a few moments just to tell you a little bit about Moyle and its history and introduce the project, and then Nathaniel will take over and take you through where we are with the project. I should say just at the moment, we're right in the middle of the project. We're at a point where the equipment is in factory test, and we hope to move on to site early next year. But Nathaniel will take you through the detail of that. So in terms of an introduction, Moyle is a dual monopole LCC setup. We were commissioned back in 2001. It's interesting that we're the oldest HVDC link on the island. It makes us sound ancient. We're not really, we're 20-year-old. But obviously that means we're now at that stage in the asset life where we're beginning to get to midlife replacement. Certainly some of the auxiliary systems are now needing replaced. And the major project then is this control system upgrade that we'll talk about. Moyle's owned by Mutual Energy, so we're a mutualised organisation. We exist for the benefit of customers in Northern Ireland. Essentially, we're trying to keep customer bills lower by giving them access to cheaper energy from Great Britain. And back in 2001, when we started out, generally Moyle imported. So we were in a situation where energy costs in Northern Ireland were significantly higher than in GB. Interconnection with the Republic was not in place at that stage because of the loss of the 275 kV connection between Tandragee and Louth. And so Moyle was a way to give us access to that cheaper electricity from GB. But that scenario has totally changed in the last number of years. And now instead of essentially importing for the vast majority of the time, we see flows in both directions. We'll talk in a moment or two about the constraints there. But we typically export whenever there's plenty of wind, and we have too much wind essentially for the island. We're also, of course, seeing less stability in transmission grids as renewables gain in penetration. That's actually more so an issue for us in Scotland than it is here in Northern Ireland. And then finally, ancillary services is a really important part of our revenue stream now, heading for 50%, and that's hard to believe, even if you go back 5 or 6 years, that figure has grown substantially. So ancillary services are a major part of what we do now. We're a Siemens station, so we have a long-term maintenance agreement with Siemens Energy UK, and that provides for staff on site during the working week. But most importantly, it gives us a direct line back to Siemens Energy in Erlangen in Germany, where the experts reside. And reassuringly, some of the guys who originally helped design Moyle are still available. So there's a lot of expertise there that we tap into when we see any specific issues. And Moyle then is operated by System Operator for Northern Ireland. So as part of Sony's license, they provide the 24/7 operation for Moyle. So that's our converter station at Ballycronamore. As you can see, we're in quite a picturesque part of the countryside, surrounded by Game of Thrones locations for any of you who are interested in it. A very rural setting, as you can see, and it's the same in Scotland. In Scotland, we're just about 7 or 8 miles north of the ferry terminals in Lough Ryan in Glenap Estate. One of the things that we're very proud of is our reliability. We did suffer a significant problem with our cables that started in around 2010, 2011, and that was due to the design of the LV element of the cables. But that was addressed with 2 new cables in 2016. And since then, we've had enviable reliability. The station reliability is amongst the best in the world. And that's some figures there from late 19 and into 20. And even looking at those figures, which you can see are all 94% and above, some of those minor drops off were based on outages enforced on us effectively by Scottish Power on the GB side and by our own annual outage. So really good reliability figures. And in approaching the control system upgrade project, it was really key for us that we focused on that reliability and made sure that the project did no harm in the first instance. I mentioned typical flows. You can see here, this is a day from September last year, or sorry, a week from September last year. And that is pretty typical of what we've seen. So during the day, we tend to import, and at night when there's wind, we tend to export. We had 3 weeks of very, very low wind, as you know, at the start of September this year. And that resulted in significant constraints being imposed on us by the system operators to secure the network. But in normal running, that's typically what we would see. I've highlighted a couple of constraints there. So we have an import constraint of 450 on import into NI, and an export constraint of well, it was at the time 80 megawatts into Scotland. National Grid would release additional capacity beyond that on a day-ahead basis, depending on wind conditions. That 80 megawatts has now been lifted to 270. And by the end of the project next year, we expect to have 500 megawatts unconstrained flow into Scotland. And we're working with Sony at the moment to lift the 450 constraint into Northern Ireland. So we're hopeful that by 2024, we'll have 500 megawatts carefree in both directions. Moyle's configuration, what you can see there is in blue, our original cables. I mentioned that we did have problems with those cables. They were a fairly novel design back in the day, a concentric design with the outer LV protected by polyethylene. And that polyethylene ended up demonstrating brittle characteristics. And so the 2016 project addressed that by replacing the subsea sections with the new MRC cables, the metallic return conductor cables. Those meet the original cables at transition joints on our beaches. And then you can see the connections on either side to the 275 kV networks. I mentioned here in Northern Ireland, those are really strong connections. We're adjacent to 2 of the local power stations and tied in by 2 circuits into the 275 network. On the Scottish side, it's a much weaker connection. We have a single 275 connection. We're about 60 kilometers away from the nearest generation, other than wind. And so the stability on the Scottish side is much less. The fault level there is now starting to get to low levels below which an LCC converter struggles to operate efficiently. And that's one of the things that we've looked at in the control system upgrade. And just some Google Earth snapshots of our 2 stations. Typically well hidden. You might notice the one in Scotland as you drive up towards Ayr. But we're nestled away beside Ballylumford here in Northern Ireland, and as I say, Glenapa State in Scotland. In terms of the drivers for our project, obsolescence was the main thing. We were starting to see obsolescence on the key Siemens PLCs, on the optical measurement systems, one of which was upgraded some years ago, but even that HOM4 upgrade is now obsolete. We're still using Unix compact HMIs from the late 90s. Our input-output units are approaching obsolescence. I've mentioned the changing network conditions, and particularly the low short circuit levels. And then an issue that we were dealing with on our DS3 services to Sony and EirGrid, we do have a deadband. The LCC technology prevents us from operating between -15 and +15 megawatts. And for some of the fast frequency response services, that deadband was an issue. So we've come up with some novel approaches to deal with that in the upgrade. And then finally, we were really keen to get full integration with Sony once again. We had that previously, but Sony have upgraded their SCADA twice since we were commissioned. and we have fallen behind. And I suppose all of that is wrapped in a timeline that's been driven by that spate of cable issues that I mentioned between 2011 and 2016. This control system upgrade would have been carried out probably 5 years ago had we not had that issue with the cables and had to prioritise on the cable resolutions. I mentioned our ancillary services. These couple of graphs demonstrate our frequency limit control. So where we provide up to 100 megawatts of frequency limit control on the left-hand side without reversal, you can see that we have a very, very clean waveform matching the frequency drop really well. And we offer that across the complete range of DS3 services from FFR through to the tertiary offerings. We have a response there in the low hundreds of milliseconds. And that service is, you know, it's a really elegant part of what we can do for the network. But on the right-hand side, you can see the situation where we have to have a power reversal. That's a messier response. We still respond very quickly, but it's not the clean, dynamically matched response that the system operator would prefer to see. And that's one of the key things that we'll address in the control system upgrade. I'm a great believer that you can make the volts and amps do whatever you want to, but you have to get the right people involved in the project to make it all happen. And we've built a very strong team. Excuse me, on our side, we engaged Nathaniel and his colleagues in TNEI to provide the project management support. We're working with TransGrid Solutions from Canada as our client-side technical advisors, and obviously they bring a wealth of experience in HVDC to the project. We've worked closely with Arthur Cox on the legalities, and that's been a really key part of getting us through both a phase 1 and a phase 2 contract. And a really important partner in the project has been Netitude in moving from a 20-year-old Unix environment to a state-of-the-art Windows environment. We've obviously had to deal with all the cyber issues that involves, and we've liaised with the the National Centre for Cybersecurity and Netitude as our own penetration testers to make sure that the cyber design was absolutely robust. Internally, we have an executive level steering group overseeing the entire project. And then clearly there's been a lot of interaction between Sony and National Grid as our two system operators, and then with SP Energy Networks as well as our point of connection in Scotland. And I should say, you know, the relationship management in bringing all those people together has been key to the project running smoothly to date. So that's a bit of an intro to where we are today. I'm going to hand over to Nathaniel now, and he'll take you through some more detail on the project itself.
Great, thanks very much, Sam. So if you move to the next slide. So just to kind of outline what we're actually doing in the project. So I guess in terms of our functional scope, one of the key things was that the existing system does work well. A lot of the philosophies are good, and so kind of the base starting point is that the controls should be like for like. But having said that, there are additional capabilities that have been developed over the last 20 years that are now available. And as Sam mentioned, the nature of the AC grids has changed. So we've got some additional capability. So we've got additional flexibility for ancillary services. We've got controllers that deal very well with low SCL levels. There's a whole new piece on cybersecurity and how we do that robustly in a world that's only where that's going to become more and more prevalent. And we've also looked at overload. So Moyle, as Sam said, is a 500 megawatt converter by or interconnector by design. There is overload capability in the converter stations, probably less so in the cable. But we're designing to allow that overload to be utilized if some of the bottlenecks in the cable system could be overcome in future years. So it really is that long-term thinking around what will set Moyle up to do another 20 years of what it does. One of the key things is integrating with Sony's energy management system. As Sam said, they've had SCADA upgrades in the meantime that have meant that that previous functionality has been lost. It gives a complete refresher of the HMIs, the operator environment, allows us to design the screens to be as user-friendly for what we need it to be for today and for the next 15-20 years. It puts a transfer scheduler back to the TSO, and there's more robust comms infrastructure being put in place as part of this project. And it also gives more the opportunity to acquire a replica. So we go to the next page. So I won't, for the sake of time, go through this in detail, but just to say that in terms of the equipment, we're kind of replacing a lot of the control and protection equipment, and there is some work on the auxiliaries, the valve-based electronics, and thyristor voltage monitoring, and some of the measurement devices. We're looking to integrate the DTS system, so for the measurements of cable temperature along the route. And also the current system is kind of blind to the cable changes that occurred back in 2016. So giving the control system, I guess, visibility of what that cable is, that cable setup is now. Here's the next page. In terms of what that means, beyond just kind of the equipment, so there's a huge number of studies looking at how that network's changed on both sides, and production of system models for the TSOs. There's factory acceptance tests and training associated with the design as well. Obviously, it covers project management, engineering, installation, testing, and commissioning. Whilst we've got the outages, we're also going to convert one of the filters at Auchencross to a slightly different harmonic profile, just to provide some redundancy. And as I mentioned, we've got a replica as well as part of this upgrade. In terms of things that I guess are really noteworthy, so in terms of the way that the project's being delivered, it's kind of a joint effort between Siemens, German and UK entities. So the UK entity is the one that provides the kind of general day-to-day maintenance on site. So there's a lot of expertise that know that station inside out in the UK entity and the LTMA team. And the UK team will lead on the installation work on site next year. The German team provide a lot of the design expertise, and some of the commissioning expertise will be done jointly with the UK. In terms of kind of key milestones, because I feel like every HVDC project pushes boundaries in some way, this will be the first implementation of Siemens' third generation VDE. I mentioned the replica, which is it's a exact replica of the controls that will be at the station, but it will be non-redundant. But it will allow us to model going forward the interconnectors response. It would allow us to adapt to changes and to fault find as issues come up over the operational life. So it will be a really powerful tool. We'll also be trialing a cloud-based archive of TFR records and some of the SER warning messages that would again allow access from kind of remotely from the station. Just a question there on non-redundant. So the control system is a fully redundant system, so it's got a kind of a system 1 and a system 2, and if there's any problems with any of the control system at the station, say system 1 is operating at that point in time, it will automatically fail over to system 2, and that's kind of key to keeping that really high reliability figures. The replica, though, doesn't need to be redundant because it's just a test environment rather than an operational one that requires the high reliability. So hope that answers the question. And then the round power mode, this is to address Moyle's deadband issues that Sam mentioned. So currently the LCC converter doesn't operate between 0 and 15 megawatts. So what this does is it allows that power flows in that deadband of -15 to +15 megawatts, basically by transferring power in opposite directions in each of Moyle's 2 poles, and then the total power that Moyle provides is the net of those 2. So, for example, you could, if you wanted to have 10 megawatts, you could put 50 megawatts in one direction and 40 megawatts in the other direction, and your net transfer would be 10 megawatts. This is just to say that this is a kind of diagram. The numbers aren't exactly, they can be altered, but basically there's kind of transitions from that round power operation through to monopolar, and then bipole where both poles are operating, and that's all to do with optimizing losses and reactive power, and there's these kind of transition points that we can change and play around with depending on what the optimal scenario is. Okay, if you can flick on to the next point, Sam. So in terms of delivering the project, very high level program. We split the project into 2 phases. So phase 1 was a feed phase that ran from November 2018 through to April 2020. And also in that phase, we negotiated the contract for phase 2, which was the actual delivery of the project. So roughly speaking, it kind of fits into almost 1 year buckets. So you've got detailed design and manufacture in 2020, factory testing in 2021, and site testing, installation and testing next year in 2022. One of the key things, as I mentioned, during phase 1, we were procuring the next stage, the phase 2 main contract, and the feed stage was actually the feed stage was very helpful in optimizing that. It gave us good visibility as to what we really needed and crucially what we didn't. One of the key things, because Mutual is a company that's a mutualized company that kind of feeds back any profits to NI consumers, there was a real desire to get good value for money. So that helped optimize the scope, but also particularly because we were going just single source with the OEM and going through things like VEET notices, we wanted to do a bit of work to kind of do a bottom-up price approach, a top-down, reviewing the market as to what other operators paid for midlife upgrades, and that was really to make sure that the contract price was in line with expectations and similar to if it had been competitively tendered, similar kind of pressures. So if you go on to the next stage, Sam. So one of the things that we hadn't anticipated was COVID, and so one of the things, we were actually due to sign the contract in person. I think it was in mid-March 2020, and there were some very fraught discussions in the run-up. Should the Germans fly over? You know, should we be getting people meeting together? We hadn't quite gone into lockdown at that point, but we kind of saw where it was going. And in the end, we wisely bumped the contract signing to a virtual one, and this was all very novel at the time. It was a virtual signing, and so this was a kind of screenshot of the signing procedure. So if you go on to the next slide, Sam. I'm just conscious of time, so I will whip through these pretty quickly. So challenges, system models. So it's pretty straightforward to get static data for system modeling purposes, but certainly proven much more challenging to get dynamic data. We've received various reduced models from the TSOs, We've also talked to some generator neighbours and got some data for parameterizing models to make sure that we model them well for some of the more challenging studies like SSTI studies and multi-in-feed and control interaction studies, where we're looking to make sure that we don't interact in any adverse way with other dynamic power electronic controllers in the area. As we mentioned, cybersecurity has been a key element of the project. So thinking through both network architecture and the patching methodology to ensure it's kept up to date. And again, the replica really helps with that. It gives us that kind of sandbox environment for making sure that no security patches that are deployed cause any operational issues with the scheme. Document management, always the thing that trips up on any project, but I guess one of the key challenges for an upgrade project is that there is a need to merge both the new documentation with the old, because not everything gets upgraded. So some challenges there around naming conventions that have changed over the course of 20 years and just making sure that everything is consistent. So there's actually quite a big job there in terms of taking some of the old documentation and updating some of the references in it, as well as making sure that the new documentation is all as expected at the as-built stage. Next slide. Getting cliched now, but of course for a project in these timescales, we hadn't anticipated COVID-19. Negotiating a contract through uncertainties around Brexit, and at the time Siemens Energy was being spun off from Siemens AG. So all three of these kind of strands meant we weren't kept bored during those negotiations, and I think fair to say Microsoft Teams has been invaluable. I think one of the things that I always say about remote working is that you can kind of tick over and you can maintain relationships. It's harder to establish them, and so actually the fact that the whole project team had worked well together during phase one and had seen each other and met up actually set us up really well for working remotely through the bulk of phase two. Using the site knowledge of the existing O&M team has been key, and one of the challenges for us has been witnessing testing. So we have done some kind of video-based witnessing of tests, but we are now at a stage where we're able to get over to Germany. We were actually over there 2 or 3 weeks ago, and we are now back to kind of doing in-person witnessing of the factory testing. In terms of site works, there's a desire to keep Moyle operating as much as possible throughout the site works, and as having a twin monopole set up, there's a desire to kind of keep one pole operating whilst the other's being refurbished as far as possible. The O&M team are working to kind of chart existing stations, so that's taking up the floor tiles and making sure all the cables are where we expect them to be. Make sure that anything that's kind of old comms infrastructure is taken out of the way and logged and all that kind of stuff. And we've taken advantage of some of the longer routine outages that Scottish Power have imposed this year to make a good inspection of the sites. On to the next one. And so just a very high level site program for next year. You can kind of see we do have some bipole outages. We keep those as short as possible, and we basically start with pole 2. That's out for kind of around 2 months. We have a bipole outage week where we get everything kind of connected back up together. Pole 2 then goes through some tests. Pole 1 goes on outage. Pole 1 then has some power tests, and then when both poles have been upgraded, we do the bipole power tests. So that's very brief. And then just to summarize, projects, I think, are defined by the people who are on them, and we've got a great team and a lot of trusted relationships built up between the project team and key stakeholders. We've got a well-defined project, and that's well in large part due to having that kind of phase one set up. The logistics have so far been planned well, and we hope that continues. And we've had the changes of COVID, Brexit, and we've managed to overcome those, and looking forward to seeing the scheme implemented next year. So that's it from me. I'm happy to take any questions. Well, I'm conscious of time, so if Geoff wants to overrule and move on, that's fine, but happy to take questions if there's time, Geoff.
Yeah, I was thinking that maybe we'll move on to a little bit behind time, but it's very, very interesting presentation, of course. So yeah, we might move on to Jonathan, if that's okay, and his work from Greenlink.
Sure. Hey, Geoff, can you hear me okay?
Yes, yeah, we can hear you.
So thanks very much for the opportunity to present. We're very happy to do so, and it's been a good session so far. So I guess give an overview. I'm Jonathan Ruddy, for those of you who haven't met me before. Technology manager on Greenlink. Started about a month ago. So still really getting to know the project myself, but we'll give you a good overview of it here. So I guess a brief overview of the project itself. It's going to be a 504 megawatt HVDC link from, I guess, County Wexford in Ireland to Pembrokeshire in Wales.
Jonathan,
yes.
Are you sharing a presentation?
I am.
Because at the moment we can just see the video view.
Ah. Give me 1 second now. Why is that happening? Oh yeah, you actually have to hit share after you select your screen.
Okay, no, that's good.
There you go. Okay. So yeah, as I mentioned, 504 megawatt HVDC. It's a symmetrical monopole HVDC system with 320 kV DC. And it's going to be using voltage source converters. We very recently signed a EPC contract with Siemens to design the converter stations on both sides, and Sumitomo Electric to do the DC cable. So we're very excited to get going on that, and I'll show you a quick timeline in the next couple of slides. We're coming into Pembroke substation on the west side, and CIGRÉ Ireland substation in County Wexford, which those of you on the Irish system will be pretty familiar with that area of the system. It's looking like 160 kilometers approximately of marine cable, 30 kilometers of land cable, and about 1 kilometer of AC cable. So I guess the broader benefits of the project, it'll import or export enough power for 380,000 homes. It's a 450 million project with private capital investment, privately funded for Ireland and Wales. Support the growth, obviously, of renewable energy, both in Ireland and in the UK. Interconnecting the two markets and creating a strategic asset for both the UK and the Irish energy system, and actually the European energy markets as well. It has been recognised as a project of common interest by the European Union, which is very helpful to achieve the EU policy objectives in terms of climate and energy. And it will help to enhance security of supply, which is a very hot topic at the moment. An extra 500 megawatts import and export capability will be, I guess, invaluable for the system operators on the Irish side, in particular in 2024, and should hopefully, in the same way as Moyle aims to do, provide value for money with downward pressure on electricity bills, and looking like some great benefits for the local area as well. In terms of that, we're looking at 250 construction jobs in Ireland during the construction phase. And those are direct jobs, and there obviously been knock-on economic benefits in the areas with the construction teams procuring everything from diesel to hotel rooms, and everything in between that's required on the Irish side. There'll be 20 permanent Irish jobs, good investment in Wexford and the local area, and obviously it will reinforce the Irish grid, as I've mentioned. Just a brief overview of the timeline then, and how we kind of got to where we are, and what our plan is for the next 2.5 to 3 years. I guess the project started back maybe even before 2018, but in 2018 we got to sort of detailed technical and environmental studies. Marine planning applications were submitted in 2019, onshore planning applications submitted in 2020. Recently got all of those consents granted, and construction work is then to commence in 2022. So we're looking at site works in January on both sides of the interconnector, with manufacturing of some key components like cables and transformers, etc., happening in 2022. First equipment delivery in early 2023 to the Irish site, and looking at completion of the HVDC cable in June 2024, trial operation around September 2024, and completed interconnector fully operational in November 2024. We can go over some of the key features, and I have a couple of slides in this, each one with kind of more detail, but what we've got, so they've got the Great Island substation on the Irish side, and we're building obviously the converter station right adjacent to the Great Island substation and the Great Island generating station. We've got this tail station, which is just another AC station in between the Great Island station and the converter station. That will be adjacent to the converter station. It's a 220 kV AC connection on the Irish side. Then we've got the DC cable, as I mentioned, 160 kilometers DC cable, 320 kV DC. Both sides, the converter stations are identical. It'd be an indoor DC yard. On the well side, then we're coming straight into the Pembroke substation from the converter station, and that's a 400 kV AC grid connection there. So I guess a few more details on that, which might be of interest to this audience. Symmetrical monopole cable itself is a 320 kV XLPE, about 1200 millimeters squared, so it's quite a decent power carrying capability in the two cables. The offshore DC cables a bit smaller. The converter stations, compared to Moyle, it's a VSC, voltage source converter solution, instead of the conventional LCC technology. This is the same technology as EWIC employs as well, with maybe a newer generation of the control and the system involved around that. There'll be a short AC cable connecting from the Locktown, which what we're calling the tail station here, the 220 kV station, from Locktown to Great Island, and a short AC cable on the other side from the converter station to Pembroke. This Locktown tail station, it's designed and installed to EirGrid specifications, and following commissioning, it'll be owned by ESB and operated by EirGrid in a similar way to how EWIC was designed and built. I guess this is kind of an overview of the indicative converter station layout and what it's planned to look like. We've got the converter hall, is that large building there, control buildings and outbuildings around that. Then this is for the well side, actually, the 400 kV switchyard, and AC components here on the outside. You've got the AC transformers just on the outside of the converter building. And the tail station will be adjacent to this, and all the auxiliary AC components are there on the in the kind of normal AC substation layout. This is a 3D view of what the well side will look like. Pretty similar layout, just with a bit of a difference in terms of where the equipment is located. That's pretty much all we need to say on that. This is an image from Siemens of what the inside of the DC hall will look like. And I know from visiting EWIC and other converter stations that this is quite an impressive sight when you see all of this power electronics hanging from the ceiling or attached to the floor in a huge valve hall like this. Here you can see so the DC cable will come in at the back of this room, and you've got the three phases of the AC coming out here. You can just see on the top the red connections heading towards the three transformers for the three phases. So looking at the cable route and where we're coming in on the Wexford side. So for those of you familiar with the very south of Wexford and Waterford, coming in around Bag and Bun Beach, and following about 20 kilometers of road route towards the Great Islands converter station, or the Great Islands substation, which is where the converter will be. To kind of show that again on satellite view, just show that we're going through, there's a number of, I guess, design and engineering challenges here, and I'll talk about one of them. We're going to use horizontal direct drilling to get in from the beach, and burying the cable along the road. Number of challenges along with road closures and all of that great stuff to liaise with the local community on, and we're currently planning all of that, and we'll be following up on that with the local communities soon. This is where the converter station is, and if I don't have it at the moment, but an image of, you'll see that the actual Great Island gas station is there as well, and the same plot as the substation, which is what, and the converter station will be beside. However, I guess the onshore cable installation, this is what the onshore cable, DC cable installation is going to look like. It's buried about 850 millimeters deep in ducts, and the two cables themselves will be buried about 300 millimeters apart from each other, and generally along existing roads. Two cables in a single trench, with the protective cover and a fiber optic cable for the controls. Then on the offshore side of things, we're using a bundled cable arrangement. So the two power cables and one fiber optic cable are being bundled together and buried along the seafloor, along the route that you see here. So this route, this cable will be buried in two campaigns, and the cable will be jointed together after the end of the two campaigns on the middle of the ocean. It'll be buried with a combination of jetting and trenching, and for those of you who don't really know what trenching is, it's a very, very interesting type of machine where you've essentially got a machine on tracks with a thing that looks like a chainsaw on the front of it, and it digs out a trench about whatever depth you require, approximately 1 meter, and knocks the cable in behind, which is an interesting thing to see on the seafloor. And then finally, one of the biggest engineering challenges that are one of the most interesting, I guess from a civil point of view, is this horizontal direct drilling. So we're not going to dig through the beach at either side. So we're using horizontal direct drilling to drill from a field, I guess, on land, down to about 10 meters below sea level, and out to the cable lay vessel, and we're going to pull ducts back through and then pull the cable through those ducts. So that's a really interesting engineering challenge behind the cable installation on this. So that was really all that I was planning to say, and I hope that I've kind of given a good overview on the Greenlink project. Happy to take any questions if we do have time. I hope that I made you up some time there as well, Geoff.
Yes, I think you have. So yeah, we've got time for one or two questions. So yeah, if anyone wants to ask a question, yeah, please ask. Okay, well, I've got one maybe. Yeah. Just, I saw at the very top of your satellite photo that looked like the DC cable split for the last kind of last kilometer or so. Do you know why that is? Just see, yeah.
Here, no, that's just a planning photo. So it doesn't split.
Okay. And the other thing is, do you know if you've got a DTS on your cable, and do you know how much coverage you're going to have?
I actually don't know that myself.
Okay.
But I would be able to.
Okay, no, that's okay.
Cheers.
Okay, so just make sure anyone else has got any questions. If you have, please fire. I think there's one from Ben.
Yes. So yeah, Ben, good to hear from you again. So VSC HVDC control ambitions in the design, black start, grid forming, plans to multi-terminal. So yes, black start, yes, for sure, we'll be in there. We're still involved in the detailed design process, Ben. So a lot of this will be ironed out over the next kind of 6 to 8 months with the EPC contractor as we go through that process.
Okay, and I'll just see there's a comment from Sam to share some of the DTS experience.
Appreciate that, Sam. Thanks.
Yeah, catch up with him. Okay, well, in that case, we might move on to the last presentation, which is from Karl. Hi, Karl.
Hi, Geoff.
Oh, there you go. Yep, we can see your screen now.
Hey. Just setting up there, bear with me. I found this laser pointer, might come in useful. Okay, is that good, Geoff? You can see my slides?
Yeah, you can just see the front slide with a kind of a beach and
yeah,
your name and stuff. Yep.
Great stuff. Okay, very good. My name is Karl O'Keeffe. Good afternoon, everybody. And I'm the asset manager for East West Interconnector and the operations and maintenance lead for Celtic Interconnector development. The picture you have before you actually is a picture of my hometown in Youghal. I grew up there about 5 kilometers away from the beach, and this is the beach for the proposed landing point for Celtic Interconnector. In the picture, you can see coastal protection in the near shore, in around here. And you can see also the timber posts applied to stop sediment movement of the beach. Similar techniques used for submarine cable protection, which we'll get into a little bit further. So I'd like to share my experiences of Ireland's interconnection, looking at the past, present and future. These 3 pictures of Ireland depict the present submarine installations for the telecommunications, gas and electricity utility sectors. There are a lot of history with each of these energy developments, and they are significant infrastructure which enrich our lives today. The first transatlantic cable crossing was connected to Valentia Island, from Valentia Island to Trinity Bay, Newfoundland, about 163 years ago in 1858. And this DC system was made up of 70 cells at 1.1 volts, each used with a single cable and a C return path. But due to excessive overvoltage, and the system only lasted for 6 days and delivered telegraphs at a rate of a few words per hour. Lots of lessons have been learned since that installation, but a lot of the theory still applies today. A lot of history has passed since that project, and fibre development has been ongoing since the late 1980s and is used for data management on the island, with over 20 connections installed and new connections planned. The gas interconnectors were constructed between Gormanstown and Moffat in 1993 and 2002 and account for about 93% of Ireland's natural gas demand. As a result of technology evolution and the maturing of Moore's law, electricity interconnectors were delivered in 2001 with Moyle using current source converter technology and thyristor technology, and EWIC in 2012 using voltage source technology with IGBTs transistors. These industries are closely interlinked and contribute to energy use on the island. And it's important to ensure that these industries continue to work together to overcome supply and demand challenges. There are many benefits to interconnection. Sustainable energy facilitates transition to low carbon futures. Competition allows for increased energy trading and downward pressure on energy costs. Security of supply is improved with diverse source of energy. And the energy union and interconnector markets will supply large-scale renewable energy resources around Europe. Fibre optics for direct communication path increase resiliency and grow the data industry. And community engagement and funds are an important feature of large-scale project development. The East-West Interconnector became operational in 2012, and this is a HVDC technology provided by ABB at the time, now Hitachi ABB Power Grids. It consists of 2 converter stations in Portan in Batterstone, County Meath, and Chotton Converter Station in Flintshire, Wales. The stations are not manned and are remotely operated by the National Control Centre in EirGrid, who dispatch the link on a 24/7 basis. Standby maintenance and repair teams are available should any issues arise. The EWIC HVDC cables are rated at ± 200 kV, they total 265 kilometers end to end, 44.5 kilometers in Ireland on land, 186 kilometers of marine, and 34 kilometers in Wales. The cables are cross-linked polyethylene, XLPE, and are made of copper and aluminium, as you can see there, these 2 cables. To connect to the transmission systems, there's 5 kilometers of 400 kV AC cable in Wales and 0.5 kilometers of 400 kV AC cable in Ireland. That's the AC cable there. Fiber optic cables, this fiber optic cable here, are bundled with the power cables and allow for robust communications between the converter stations. It also allows for fast acting response to system events such as frequency control. And the fiber connection also provides a resilient communication path between that the TSOs can use and rely upon during blackouts. We also use the fibers for DTS monitoring of the cable with a number of redundant fibers. And there's also a commercial fiber lease with Geo Networks. The repair preparedness facility is strategically located in a secure deep water port in Liverpool, just around there. And this allows for quick mobilization of offshore repair in the event of a cable fault. In the picture, you can see 10 kilometers of marine cable spare on a carousel in a controlled environment, and routine maintenance consists of ensuring that the mechanical devices remain operational and the asset is secure. For the management of EWIC asset, we adopt best practice ISO 55001 asset management with integrated risk review. The scope of the asset management system accounts for key aspects such as external factors and stakeholders, the organization and the asset details. Regular features of our operations include strategy and planning, organization structures, the life cycle of the asset information, decision making. We conduct regular risk reviews. Some of the active risks being managed are safety, asset availability, cable strikes, physical security, legal and contractual matters. During COVID, this asset management system allowed the team to manage through uncertainty and reprogram outages and maintenance plans in a flexible and agile manner. We pride ourselves in our safety and operational standards. This picture was from a safety conference in 2018 and shows probably half the number of persons involved in the operations and maintenance of the asset. Our organization structure is an outsourced model relying on the necessary expertise as needed. The converter maintenance and repair contracts are in place with Hitachi ABB Power Grids. A service level agreement for cable repairs is in place with NKT. As part of this agreement, there is a secured guaranteed vessel availability of the Victoria vessel to ensure fast repair operations. There are a number of subcontractors that we also rely upon, including cable monitoring and awareness training, physical and cyber security. During COVID, we have maintained safety and operations excellence in an agile, flexible manner, and this has resulted in a greater than 98% availability of the asset, and it's a great result by the team. There's a lot of equipment at the converter station designed with redundancy to operate for over 8,584 hours of operation in a year. To realize this, full redundant control and protection and power systems are required, and this is located in the building. Sorry, I'll just move something here. This building here. The MAC2 controller is at the heart of the control of the interconnector responding to system events. The asset is maintained on an annual basis in what's best described as a 84-hour pit stop. Motivated specialist crews review and inspect the assets and replace components as required. So it's important to have a fully equipped on-site spares facility located here. With the strategic importance of the asset, a transformer fault is mitigated with an upfront capital cost of a strategic spare. This minimizes unavailability of the asset in such events and improves business continuity. The spare transformer is located here. The asset is designated critical infrastructure under NIS-D, the Directive on Security on Network and Information Systems. In addition to a number of cybersecurity initiatives, we have made investments to enhance physical security on site. That's the physical security perimeter fence that we have. The East-West Interconnector is a voltage source converter which can independently control active and reactive power. With such technologies, a voltage reference can be applied to a black network with the support of a standby diesel generator. The black start functionality is provided to both EirGrid and National Grid ESO, and the diesel generator is located here. This is a Generation 3 VSC converter from Hitachi ABB Power Grids. It consists of a series connected IGBTs that requires full pulse width modulation. This results in higher switching losses and harmonic challenges. To break it down, the picture shows the inside of the valve hall where switching operations occur. There are 3 valves, VA, VB, VC, which are replicated in each of the converter stations. The valves are suspended from the ceiling and are made up of 32 IGBT stacks. Each stack has around 25 IGBT modules, and in total there are about 2,500 IGBTs in a converter station. Each IGBT has an excess of about 100 components made from transistor and diode semiconductors and mechanical components within the stack pack. During switching operations, temperatures within the valve hall can reach about 70 degrees Celsius, and the valve systems are being force cooled by 2,000 liters of high pressure glycol. When not in operation, all these areas within the valve hall need to be routinely inspected and maintained, where working height is a risk. In the near 10 years of operation, Moore's law continues, and this generation of valve design has moved on. In today's world, multi-level VSC converters result in more efficiencies with lower losses, as an example. In 2019, MMT performed one of our routine geophysical surveys over the entire EWIC cable route. This builds on the previous survey completed in 2015. Multi-beam, echo sounder and side-scan sonar techniques are used to assess the burial condition of the cable and any changes at the cable's position, current protection and environmental conditions. Whilst the majority of the route was fine and our existing protection remained unchanged, in this picture here, you can see a cable exposure was identified. The team conducted a cable integrity risk assessment and assessed this and any other potential areas of concern. Remedial works were carried out using NKT Victoria in late 2020, where we installed precise rock placement bags over specific locations of the EWIC HVDC cables. In total, over 265 PRP units weighing 2 to 4 tons were installed to provide additional external protection and mitigate the risk of third-party damage. In the picture, you can see the fronded and unfronded rock bags on the ship's deck and offloading of the rock protection and the installation survey following the installation. It is exciting times for HVDC interconnection in Ireland. There's 1.2 gigawatts of projects in development between Greenlink and Celtic Interconnectors. And with each new interconnector, existing interconnectors will need to adapt and be flexible for new operating regimes. The Celtic Interconnector project is a joint project between EirGrid and RTE in France. This is the first electrical connection between Ireland and France. It's a project of common interest status from the EU since 2013, and it is a national strategic importance. We are presently in the details and design and consents phase of the project, and the construction phase is between 2022 and 2026. The specification of the project is similar to that of EWIC. It will be a VSC converter with newer technology. It will have higher capacity of 700 megawatts. The cable voltage will be 320 kV and will have a fiber connection. RTE is the largest TSO in Europe, and it is really great and interesting to work with their teams. Our engineering challenges are very, very similar. If you haven't already been aware, EirGrid is stepping up as a new offshore transmission asset owner role in support of the government's climate action ambitions. In Ireland, the sea area is 7 times larger than the landmass, and there is high potential for offshore RES. Offshore wind delivers higher and more consistent wind speeds. The planning and development of the offshore grid assets will enable the operation of the offshore wind farms and will play a central role in harnessing the unique resource. Interconnection and offshore grids interoperability will play a significant role to realise the energy union. The NSOE report, this one here, produced in January 2021, tasked policymakers and TSOs and manufacturers regarding legal and regulatory governance, funding and demonstration projects, how to adapt planning approaches, the concept of standardizing equipment for plug and play concepts, and also to have multi-vendor cooperation agreements. So our purpose in EirGrid is to transform the power system for future generations. I hope you have been inspired with some of the highlights from today and look forward to the challenges we can solve together to realise 70% RESI by 2030. And happy to take questions.
Maybe a question from me, Karl. For the offshore connections, is there any kind of timeline when those are expected to arrive?
Yeah, so there's a number of projects in development. There's quite a lot of activity on the East Coast, and the various projects have various connection and target timelines within the next 5 to 6 years. And it is expected that additional 10,000 megawatts of wind will connect to the system by 2030. So over the next kind of nine years, there's going to be significant transformation of the power system.
Okay, thank you. And I see Jonathan's got his hand raised. So Jonathan, do you have a question?
Sure.
Thanks. Hi, Karl. Thanks for that. You mentioned there about the UA cable and being 265 PRP bags dropped. Do you know what kind of distance of cable or length of cable that was covering?
Okay, so it was a 6-meter exposure, but on top of that, there were a number, there's quite a lot of sediment movement and sand waves that is active over the UA cable. I don't have that figure top of my head, Jonathan. I'd have to work it out and look through the project material. But yeah, it was a successful project. And I suppose the 4-ton bags, maybe we'll try and work it out. There were, maybe 2 to 3 meters spanning in length. Multiply that by the 265, so up to about what's that, kilometer?
Okay, yeah, that's fair. Thanks.
Okay, we've got one more question in the chat. So I can read it out. For a smart valve, would the installation typically be in a substation? I assume it goes in series with the line, so what are the space considerations? The pictures from the project in the UK look like substantial installation. What possible several smart, so this is for the not for your presentation, Karl, this is for the original, for the smart valve presentation. Are they still on the line, Marie?
Yeah. Hi there. So they are typically carried out in substations. They're not insignificant devices. Rob might be able to chime in with the dimensions of an individual box. That said, I think in the picture we showed earlier on, you saw 2 devices in series. You can also stack these vertically. So in fact, that site at National Grid, we've installed 2 devices per phase, and next year we're going back and installing another 2 devices per phase on top of the existing one, so there's no increase in footprint. You can also split the installation, as Rob mentioned, between both ends of the line at both stations, or indeed you can create or install them midway along the line. So there's a lot of flexibility in how you physically install them and connect them in series with the line. Rob, are you on call? Could you chip in with some of the dimensions, perhaps?
Yeah, so each individual device is about 5 meters in length and then 2 meters tall and 2 meters wide. That's the rough dimensions of it. And as you said, they're stacked up similar to what some of the photos shown for the HVDC stations, where you have the converters stacked on top of each other. That's sort of our plan as well, to have those devices stacked on top of each other in a similar way.
Okay, yeah, thank you for that. And I see there's a couple of more questions for you, Karl. If you do you want to read those? And there's one from Ben and one from Paul O'Rourke.
So Ben, okay, 2 seconds there. Okay, so there's a question in there on the offshore grids, and I would say it's very much at conceptual stage. There's quite a lot of details in there, and very good suggestions. Okay, yeah, there's Ben, that's very good. Sorry, I'm reading the chat and I'm sure everybody else can see that chat there, and there's quite a lot of details in there, but I would say that EirGrid is in development of this role, and will be engaging with all the necessary stakeholders, and some of this feedback would be very useful. Paul O'Rourke, hi Paul, how are things? Great to see the availability stats so high, and I'm assuming it means that you've no cable faults, touch wood, thank you. Yes, actually the cable asset has been the best performing element of the asset. It has been taken out of warranty, and that's why we have a service level agreement in place with NKT, with significant repair and response times in there. And as I mentioned, we've that guaranteed availability of the Victoria vessel, which is a DP3 vessel, which has the ability to repair when there's somewhat troubled waters. And the availability has been very good for the last year. So thanks, Paul.
Okay, so maybe I don't see there's any more questions. So thank you, Karl, for that presentation. And I guess this kind of brings a close to the seminar. So thank you for all the presenters who did a great job in your presentations. And thank you to Jason for hosting the Zoom session. And also, of course, thank you to Marta, who of course is working behind the scenes as she does, and you think that's CIGRÉ Ireland. So yeah, so I guess we can call it this session to a close. So thank you very much for all taking part.